On October 19, 2017, a day that would forever change our understanding of the cosmos, the Pan-STARRS 1 telescope in Hawaii, perched atop the Haleakala Observatory, was diligently scanning the heavens. This powerful telescope, designed to detect near-Earth objects, was about to stumble upon something far more extraordinary. It detected a faint, fast-moving object, a mere speck of light against the vast darkness of space. But this was no ordinary asteroid or comet. Its speed and trajectory were unlike anything astronomers had ever seen before. It was clear from the outset that this object was something truly special, something that defied easy categorization. Its trajectory was a hyperbola, a curve that indicated it wasn't orbiting our sun in a closed loop. This trajectory was definitive proof it wasn't gravitationally bound to our sun. It was just passing through, a fleeting visitor on an interstellar journey. This realization sent ripples of excitement through the astronomical community. This was it, our first confirmed visitor from another star system, a tangible piece of another world entering our own. It was a moment of profound significance, a milestone in our exploration of the universe. Astronomers, recognizing the importance of this discovery, named it Oumuamua, a name that comes from the Hawaiian language meaning scout, or more poetically, messenger from afar arriving first, a fitting tribute to its pioneering role. The name perfectly captured its profound significance, a harbinger of a new era in astronomy. It was as if the universe was offering us a handshake, a chance to examine matter from another star's planetary system up close. For centuries, humanity has gazed at the stars, wondering what secrets they held and what lay beyond the confines of our solar system. Now, a piece of that unknown, a messenger from the stars, had finally come to us, bridging the vast gulf between worlds. Its formal designation, 1I/2017 U1, a string of characters that belied its extraordinary nature, officially marked it as the first of a brand new interstellar category of celestial objects. Before Oumuamua, every asteroid, comet, and planet we had ever studied was a native of our own solar system, born from the same cloud of gas and dust that birthed our sun. This was different. This was an immigrant, a traveler from a distant land, a galactic tourist, briefly gracing our corner of the universe with its presence. Its arrival served as confirmation that the process of planetary formation around other stars inevitably ejects debris, fragments of worlds, into the vast emptiness of interstellar space, creating a cosmic diaspora. With this discovery, we were no longer isolated in our solar system, but rather an integral part of a vast, interconnected cosmic ocean, sharing our space with countless other worlds. The discovery of Oumuamua was not only a technical triumph, a testament to the power of our telescopes and the ingenuity of our scientists, but also a profound inspiration, a reminder of the boundless wonders that await us in the universe. Oumuamua's fleeting passage through our solar system was like a cosmic message in a bottle, a tangible link to a distant star system, a world we may never be able to reach, yet now feel connected to in a profound way. It invited us to look at the night sky with new eyes, to see it not as a distant, unreachable void, but as a vibrant neighborhood teeming with unseen possibilities, a galactic community of which we are a part. Astronomers long suspected our solar system wasn't isolated, other stars must eject debris too. The galaxy should be filled with these cosmic nomads, but finding one is incredibly difficult. Oumuamua's discovery was a triumph of technology and luck, a one-in-a-million catch. Its existence proved that the building blocks of planets are exchanged between star systems. Could life itself travel this way? While Oumuamua showed no signs of life, its presence raises tantalizing questions. Each interstellar object is a physical sample from another world. Studying them lets us learn about distant star systems without leaving home. Oumuamua transformed interstellar object searches from theory to reality, spurring new urgency for better telescopes. The age of interstellar archaeology had begun, with Oumuamua as its first artifact. As astronomers tracked Oumuamua, its strangeness grew. Its brightness fluctuated dramatically, suggesting an extremely elongated or flat shape, unlike any known asteroid or comet. It tumbled chaotically, not rotating smoothly like most solar system objects. This hinted at a violent past, perhaps a collision or chaotic ejection from its home system. Oumuamua sped through space at 26 kilometers per second, accelerating to 87 kilometers per s near the sun. Unlike comets, it showed no tail or outgassing, even under close observation. Its surface was reddish and surprisingly reflective, yet it was completely inert. These traits, extreme shape, chaotic motion, high speed, and lack of outgassing set it apart from anything we knew. It didn't fit our categories of comet or asteroid. Each new observation deepened the mystery. Oumuamua was a cosmic enigma, challenging our assumptions about the galaxy's contents. As Oumuamua left the solar system, astronomers noticed it was accelerating, moving faster than gravity alone could explain. Normally, comets accelerate by venting gas near the sun, but Oumuamua showed no visible outgassing or tail. The Spitzer Space Telescope saw nothing. No coma, no dust. If gas was venting, it was invisible to our instruments. This contradiction baffled scientists. It accelerated like a comet but looked nothing like one. Usual suspects like water or carbon dioxide were ruled out. The mystery forced theorists to consider exotic possibilities. This unexplained push became the focal point of the Oumuamua debate. It was a direct challenge to our understanding of celestial mechanics. The quest to explain this whisper from the void ignited one of astronomy's most exciting debates. Faced with a cosmic mystery, a puzzle that defied easy explanation, scientists embarked on a quest for answers, proposing theories ranging from the mundane, rooted in known physics, to the extraordinary, venturing into the realm of the speculative. Each idea was an attempt to make sense of the anomaly. Harvard's Avi Loeb, never one to shy away from bold ideas, suggested the possibility that Oumuamua could be a piece of discarded alien technology, a derelict spacecraft, or even a probe sent to observe our solar system. Specifically, he posited it might be a solar sail, a vast thin sheet designed to be propelled through space by the pressure of starlight. However, most scientists, while acknowledging the allure of such ideas, sought natural explanations, phenomena that could be understood within the existing framework of astrophysics. One intriguing idea was that Oumuamua was, in fact, a hydrogen iceberg, sublimating invisible gas as it warmed near the sun. This process could explain the acceleration without a visible tail, but such a fragile object, composed primarily of hydrogen ice, would likely erode and disintegrate long before reaching our corner of the galaxy. Another compelling theory proposed the existence of a dark comet, a water-rich body trapping significant amounts of molecular hydrogen within its icy structure, which was then released as it neared the sun, providing a gentle, consistent push, explaining the observed acceleration without the telltale sign of a visible coma or tail. This explanation elegantly fits both the observed acceleration and the perplexing lack of visible outgassing. However, no definitive consensus exists within the scientific community. Each proposed theory possesses its own strengths, explaining certain aspects of Oumuamua's behavior while simultaneously exhibiting weaknesses in other areas. The tantalizing idea of an alien probe, while undeniably thrilling, remains firmly in the realm of speculation, lacking any concrete evidence. The hydrogen iceberg hypothesis, while clever in its explanation of acceleration, struggles with the inherent fragility of such an object. The dark comet theory, on the other hand, finds support in laboratory experiments simulating the behavior of molecular hydrogen under space-like conditions, aligning with other astronomical observations. Ultimately, Oumuamua forced the scientific community to think creatively and challenge existing assumptions, pushing the very limits of our knowledge and understanding of the universe. Oumuamua wasn't the last interstellar visitor. In 2019, 2I/Borisov was discovered behaving like a typical comet, unlike Oumuamua. Its normalcy highlighted how bizarre Oumuamua truly was. Some near-Earth objects also show unexplained acceleration without visible comas, possible dark comets. Japan's Hayabusa 2 will visit one such object, 1998 KY-26, in 2031 to study this phenomenon up close. The European Space Agency's Comet Interceptor, launching in 2029, will wait in space to intercept the next pristine comet or interstellar object. These missions mark a shift. We're now preparing to meet these visitors, not just observe them. The discoveries of Oumuamua and Borisov have opened a new field, comparative planetology beyond our solar system. Each new object is another piece of the cosmic puzzle. We're beginning to build a galactic picture of planetary evolution. Oumuamua's visit was brief, just weeks in range before fading into darkness. Astronomers traced its path, but its true origin remains unknown. Vega was a candidate, but the timing didn't fit. Now it's over 6 billion kilometers away, far beyond Neptune and invisible to our telescopes. We'll never see it again. It's heading toward Pegasus, destined to wander the galaxy for millions of years. Its fate is uncertain. It may stabilize, be altered by cosmic rays, collide, or drift forever. Its story reminds us of our fleeting moment in the cosmos. We witnessed just one act of its epic journey. Without knowing its origin, we can't know what created it. Oumuamua remains a sample without a label, a message without a return address. The perplexing nature of Oumuamua, with its unusual trajectory and shape, ignited the imaginations of scientists and engineers worldwide. This interstellar interloper sparked a wave of innovative thinking, and among the most ambitious ideas was Project Lyra. Project Lyra proposed nothing less than an audacious mission to chase it down with a dedicated spacecraft, a feat of engineering and interstellar navigation. The mission concept involved a complex series of maneuvers, using gravity assists from planets like Jupiter to slingshot the spacecraft towards its distant target, and a daring solar slingshot, also known as an Oberth maneuver, to gain maximum velocity. The challenges inherent in such a mission are immense, requiring not only high speeds to reach Oumuamua in a reasonable time frame, but also advanced propulsion systems capable of sustained acceleration over vast distances. Concepts like ion drives and even nuclear propulsion have been considered. Furthermore, the mission demands extremely precise calculations and tight launch windows, dictated by the ever-changing positions of both Earth and the target object. Even with the most optimistic projections, the fastest missions employing cutting-edge technology would still take decades to catch up with a fleeting interstellar object like Oumuamua. But the potential scientific payoff, the knowledge gained from such an endeavor, from obtaining an up-close look at Oumuamua, analyzing its composition and understanding its origins, would be immense, potentially revolutionizing our understanding of planet formation and the prevalence of life beyond our solar system. While chasing down the first discovered interstellar object may remain a dream, at least for now, our ability to find its successors, to detect and characterize future interstellar visitors, is about to leap forward dramatically. The Vera C. Rubin Observatory, a next-generation astronomical facility, is poised to begin its groundbreaking operations in 2025, ushering in a new era of astronomical discovery. It will systematically scan the entire visible sky, night after night, searching for transient events and, crucially, interstellar objects. Experts predict that it could detect dozens of Oumuamua-like visitors each year, a significant increase from our current detection rate. This abundance of detections will give us significantly more time to study each object in detail, allowing for comprehensive characterization before they fade back into interstellar space. This unprecedented flood of data, a treasure trove of astronomical information, will fundamentally transform the field of interstellar studies, elevating it from a realm of speculation based on a single anomaly to a robust and data-driven science, grounded in observation and analysis. With a larger sample size, we'll finally be able to determine if Oumuamua was truly unique, a cosmic oddity, or simply the first member of a much larger population of interstellar objects constantly traversing the galaxy. And who knows, next time one of these cosmic messengers appears, we might just be ready with a spacecraft to meet it. Oumuamua's visit was a catalyst for a paradigm shift. It shattered our sense of cosmic isolation and opened our eyes to an interconnected galaxy. This single object inspired new theories, technologies, and missions. The big questions remain: what is it? Where did it come from? What can it teach us? Studying interstellar visitors is galactic archaeology, piecing together the story of other worlds. Oumuamua is a symbol of the mysteries that drive us to explore. Its legacy is a new frontier where the space between stars is filled with stories waiting to be heard. And now, we are finally ready to listen.